Okay, gang, let's now do continuity in terms of when you're just given a function and there's no graph. This part really is going to weigh heavy on how good your pre-calc and intermediate algebra skills are. Students that have a strong foundation with their previous courses, that's what you want to lean into when you do this, okay? This is, you really want to lean into your toolbox to figure these out. All right, so now the first one, the idea for this one is you're basically looking at these and you're trying to figure out, does this have a hole? Does this have a gap? Does this have a vertical asymptote? You know, like what kind of problems does this have? Does it have a point? Stuff like that. So when I see this, my first inclination here is to factor it. All right, and because it has common factors, this is actually a case of a linear line with a hole in it when x is 2. So when x is 2, right here. So this one, in terms of discontinuity, has a discontinuity at x equals to 2, because that's where it becomes 0 over 0. And I'm going to label it as removable because it's a hole. Remember, common factors most of the time make a hole. All right, let's take a look at this one. So I'm going to graph this in parts so you can see the whole thing. This here is 1 over x squared. That is always positive. So it sort of looks like this. It looks like a volcano. Okay, it sort of looks like that. Now this says that this function x cannot equal to 0. And the function below it's 0, it says x can be 1. So this right here is saying that you have a point. So it may look to somebody who doesn't really have a sense of what they're looking at as maybe there's a problem, but it was fixed. But this has a vertical asymptote, and you can't plug a vertical asymptote with a point. It doesn't work like that. So we would say for this one that it has a discontinuity at 0, right? Everywhere else it's fine. It's just at 0. And because it's a vertical asymptote, it becomes unbounded. We call this non-removable, okay? And that's again because it has a VA. All right, let's try another one. So this, if we think about this, this is some sort of face-up parabola, but it's saying that I can't use when x is 2. So I'm just going to guess that maybe x is 2 is somewhere over here. You just have to get a gist of what you're looking at. You don't have to have it exact, okay? Just like an idea. So it's saying I can't use some point 2. So it's important to know like where that point is that you can't use. All right, so if I put 2 in here, I'll figure out what the height of that is. All right, so that's 4 minus 2 minus 2. That's going to end up being 0. So that when I plug in 2 into here, I'm going to actually get out 0. So the question is, does this other point at 2 plug the hole? What do we think? No, it doesn't, right? Because then they give us another point, an input of 2, and output of 1. It's going to sit above the hole and it's not going to plug it. If they plugged the hole, then it would have made it continuous, but they didn't plug the hole. They put a point above it. So we would say here for this one that we have a discontinuity at x equals to 2, and it's removable because it's a hole. It's really important, and I think when I grade these, that you tell me where the hole is. I want to know that you can figure out where the problem is as well as what kind of problem it is, whether it's removable or non-removable, okay? But make sure on the test and the final you say where the issue is, where the VA is, where the gap is, where the hole is. All right. This guy here is your step function. So remember your step function, if it's not modified, the initial step will start right here at 0, and it'll jump up every integer. Okay, so it's a set of steps. So in terms of discontinuity, it has an infinite amount of gaps, but the gaps always fall where? Where do the gaps always fall? It jumps up at every integer. So it has a discontinuity at every integer. And that discontinuity would be non-removable because it's a gap. Let me just grab one more while we're at it. Let me make it up. Let's say you have the tangent of x, right? Y equals the tangent of x. Now we know this is a discontinuous function. Actually, let me make it harder. Tangent of 2x. Now we know this is a discontinuous function. So let's first now break it into its quotient identity. Now we know the VAs are going to occur when cosine of 2x equals to 0 because the fraction becomes undefined. So the vertical asymptotes are going to occur when cosine of 2x equals to 0. There's a lot of pre-calc here. A lot of pre-calc in this section. So first of all, if you remember from pre-calc, you ignore the 2x for a moment. You just try to figure out where the cosine is 0. And if you recall, it's going to happen at every fractional pi as you go around the unit circle. So in standard position, you hit the first one. You hit the first answer at pi over 2 in standard position. Okay, again, I'm pretending it's a cosine, just a plain cosine x at the moment. So I hit the first one at pi over 2, and then I have to jump a distance of pi to get to the next one, and a distance of pi. So like when you're on the merry-go-round, you're going to stop here and here, and the distance for me to move from here to here is pi, right? So I have to add pi n. Remember, n is an integer, so when n is 1, this is 1 pi. When n is 2, this is 2 pi. Because you have to keep moving around you have to keep moving around the circle. All right, now the problem is that this is an x, this is 2x. So really at the very end is where you counterbalance whether the function has been sped up or slowed down. So this function has been sped up. So at the very end, I'm going to just balance that out. So it's going to be x pi over 4 plus pi n over 2. All right, so in terms of discontinuity, I found where the VAs are. So we have a discontinuity at x equals to pi over 4 plus pi n over 2. And these are non-removable because they're vertical asymptotes. All right, if you get stuck on the trig, and there is trig, there's logs, there's exponentials. If you get stuck on something, just shoot me an email, okay? This section is a bit more work than the others, so don't wait till the last minute to do it. You really want to like get in the trenches with this one and like work it, spend a good amount of time in this section. All right, gang, I'm going to come back and do one other little piece for this section, and then we'll be done. Catch you. Bye-bye.